Welcome to the History of Relativity series. Today, we will talk about the last part of Einstein's accomplishments, the formation of the general theory of relativity. Last episode, we demonstrated that the special principle of relativity was valid in the same way in which we proved that the Galilean principle of relativity was valid. That is, by showing that the rejection of the principles would violate causality, one of our fundamental principles. Einstein, in his third paper of 1905, showed that there was a causality problem between Maxwell's electrodynamics and Galilean relativity, and that the only true issue was that Galilean relativity was unable to measure the speed of light, and therefore unable to see that as objects increase in velocity towards the speed of light, that a factor needs to be introduced to keep the speed of light constant. It was, however, Einstein's fourth paper of 1905 that brings us here today, and brings us into the theory of general relativity. After Einstein introduced special relativity by finding a problem between Maxwell and Galileo, he kind of repeats this process by attacking himself and his special principle of relativity, as there must be an effect on the principle of the conservation of energy, which might not be good. His fourth paper is very short, containing in the English translation only 717 words. As such, allow me to translate the English translation into something a little more digestible. The results of the previous investigation lead to a very interesting conclusion, which is here to be deduced. I based that investigation on the Maxwell-Hertz equations for empty space, together with the Maxwellian expressions for the electromagnetic energy of space, and, in addition, the principle of relativity. With these principles as my basis, I deduced the following results. Let there be a system of plane waves of light possessing the energy L in the system of coordinates S. If we introduce a new system of coordinates, S', moving in uniform parallel motion with respect to the system S, then, according to the system S', this quantity of light possesses the energy L times a relativistic shift. Let there be a stationary body in the system S, and let its energy in the system S be called E0. Let the energy of the body relative to the system S', moving as above with the velocity v, be called H0. Let this body, which remains at rest with respect to the system S, send out plane waves of light, of energy 1/2 L measured relatively to S in equal and opposite directions. The principle of energy conservation must apply to this process with respect to both systems of coordinates by the principle of relativity. If we call the energy of the body after the emission of light E1 or H1 respectively, measured relatively to the system S or S' respectively, then by employing the relation given above, we obtain that the energy of the stationary body at the start is equal to the energy of the stationary body after, plus 2 released packets of energy, which together have the energy L. Whereas from the S' moving frame, we measure that the original energy of the body, before sending out plane waves of light, is now equal to the energy of the body after, plus the energy of L with a relativistic adjustment. By subtraction, we obtain from these equations that the difference in the initial energies minus the final energies equals the original energy of the plane waves times gamma minus 1. The two differences of the form h minus e occurring in this expression have simple physical significations. H and E are energy values of the same body from two different systems of coordinates, which are in motion relative to each other, the body being at rest in one of the two systems, in system S. Thus it is clear that the difference h minus E can differ from the kinetic energy k of the body with respect to the other system S prime with the addition of a constant. The kinetic energy of the body with respect to S prime diminishes as a result of the emission of light, and the total decrease is independent of the properties of the body. Moreover, the difference k0 minus k1, the kinetic energy, depends on the velocity. From this equation, it directly follows that if a body gives off the energy L in the form of radiation, its mass diminishes by L over c squared. The fact that the energy withdrawn from the body becomes energy of radiation evidently makes no difference. So we are led to a more general conclusion that the mass of a body is a measure of its energy content, where L is a measure of energy. M equals E over c squared, or E equals mc squared. If the theory corresponds to the facts, radiation conveys inertia between the emitting and absorbing bodies. And with that final line, Einstein ties up all four of his 1905 papers. Having started by demonstrating Brownian motion is best explained by the existence of atoms, and then that light is a form of radiation energy which exists as quanta and can provide enough energy in a single hit when tuned properly in order to break the bonds between some metal, i.e. an atomic structure, and one of its electrons. He then proved that the motion of photons and electrons and other quantum particles are too fast for Galilean relativity to get accurate, and you need to account for that speed in terms of not just velocity, but of its components, length and time. And finally, that because of this fact of special relativity, it must also be the case that mass and energy are equivalent, and that in fact, the Brownian motion of paper 1 is caused by the fact that atoms exist as quantum particles who exchange energy through radiation, i.e. photons, and that photons are in fact a kind of massless mass-energy converter which conveys inertia between the emitting atoms and the absorbing atoms, thus moving them around. This also means that if you add energy to an object, say increase its temperature or force it near an object it is electrically repulsed from, then it will increase in mass. It also means, though, that if an object in motion perceives energy that is emitted from a body, it will perceive it with a relativistic shift. The kinetic energy of the object appears to be changed, and the laws of conservation of energy cannot allow for a loss or gain in energy without a counterbalance. Einstein thought about this for 2 years. Let us be Einstein ourselves and work this out. 1. Everywhere we go, the laws of physics are the same, even when we are in motion. 2. The speed of light is always constant. 3. Velocity is relative, and the faster our velocity, the bigger the difference in appearance of our length and time will be to others not moving along with us. 4. The faster our velocity, the bigger the apparent difference of kinetic energy, and therefore the bigger the apparent difference of mass to an observer who is not in our frame of reference. 5. Typically, when we think about mass, we think about heaviness and falling down. Given that falling is a form of motion and is related to mass, then falling is related to energy, which we also already know as that is the difference between potential and kinetic energy of massive objects. Therefore, there must be a relativistic effect here as well. 6. However, relativity has only really dealt with constant velocities, but we know from Galileo that all objects accelerate, that is, positively change velocities over time downward, and more so, that all objects accelerate down to the Earth at the same rate. 7. It thus can also be the case that the principle of relativity applies in some fashion to accelerated reference systems. Think about it like this. Again paraphrasing Einstein, what if a gravitational field is like an electric field, which is generated by a magnetoelectric induction? What if the field only exists because of some relativistic effect? In such a field, where you are a charged particle and the electric field becomes more attractive the closer you get, you therefore accelerate towards it. What if gravity were as such? For example, if I placed you in empty space, meaning far from any other objects for millions of astronomical units, with a strong magnet in your pocket, then, somewhere in the distance, I place either a massive body or a super large magnet in the opposite polarity of yours. Before you know what the object is, you see me place something. And you see the moment that I do, that you slowly, at first, start moving towards me and the object. And over time, you start moving towards it faster and faster. Without seeing it, how would you know if you are falling towards a massive body through gravity or accelerating towards a magnet? Before we get Einstein's answer to this question, let's start back at the beginning. We've gotten so tied up with light in the supposed vacuum of space that we lost track of rocks and planets and the nature of things falling down or up back to their natural places. Let us fall back to 500 BC. Heraclitus told us that Logos keeps the cosmos in harmony, moving all objects by a kind of law, by a sort of reason. This philosophically divided the world into two halves. To some, Logos is logic and natural law, and to others, Logos is logic and consciousness. This makes sense, as in order for us conscious beings to recognize facts of reality, and therefore form rules of logic to help us further identify other facts of reality, we necessarily have to have a consciousness capable of discovering facts, and thinking, and reasoning, etc. So, depending on your metaphysical basis of reality, e.g., a belief in a god or gods or scientific reasoning of Big Bang cosmology, will shape how you view the logos of the cosmos. Is it divine reason held in place with natural laws? Or is it natural, to which we have reasoned out some laws that aid our understanding? Aristotle was under the belief that logos was here on earth, as compared to his teacher Plato, that put logos in a divine creature that saw a cosmos of disorder and decided to organize it. Aristotle, given his observations of the nature of reality on earth, found that all objects of their own kind tended to find their way to their place in the order of all things, and that in order to move something required a constant force. This then was the first philosophical theory of gravity and inertia, that it was causal by the nature of the objects. Due to the fact that Aristotle was not aware of the concept of friction, this caused him, as it does to most people, to conclude that an object at rest remains at rest until you add a force to it, and that an object in motion will come to rest without a force constantly acting on it. Or otherwise stated, an object in motion will only remain in motion while a force is applied to it. This led Aristotle to hold that objects will fall at different rates because of their mass, type, and the medium in which they are falling. Following Aristotle was the Christian theology and the dark ages they brought upon humanity for over a millennia, where the Logos became a humanoid figure with a plan to save humanity from the pain he's inflicting on them. On our first run through this timeline, we were focused on the stars in the celestial sphere as we passed from Aristotle to the Church, making those spheres levels of heaven, and the later shift in perspective that Earth was not at the center of those celestial spheres. However, this time we are exclusively focused on gravity, mass, and inertia. So we are going to take a detour to the Islamic world around the year 1000. Here we meet a prominent figure in philosophy and science, and whose accomplishments are typically passed off as being some European's accomplishment. The hero of this era goes by the name Avicenna, or as he is known by the Latin corruption of his name, Avicenna. Avicenna, in his philosophical encyclopedia, The Book of Healing, which is not a medical text, but rather a metaphorical healing of the soul through scientific experimentation and examination, provided us the philosophical thought experiment that Descartes would later utilize and get full credit for. Avicenna, and 600 years later Descartes, constructs a thought experiment called the floating man. He speculated on what a man detached from objects of perception would be like. He's floating, without air pushing him or pressing against him. He cannot see or taste or touch or smell or hear anything. Can the man be self-aware of his existence in this floating space? Despite this topic historically swerving into ontology, epistemology, and psychology, this exact thought experiment will show up again with Einstein in 900 years. Both Avicenna and Descartes conclude, quite illogically, that the man must be self-aware. He, according to them, thinks, and therefore he is, and he does so because God. Well, that will not be much use to us at the moment, but we will stick a pin in this floating man thought experiment and use it for something else later. What was most important from Avicenna at this time, however, was the conclusion he made about motion, which again Descartes would take 600 years later, but would not get the credit as Newton scooped it from Descartes in a like fashion. Avicenna disagreed with Aristotle, and rightfully so, and distinguished the difference between an object moving due to its inclination to its natural state and a force applied to an object, and that the inclination of motion on an object is in fact imparted to it by a force. That an object thrown by a man will have its energy of motion come from the logos of the man throwing it, and that the object will continue to move at that constant velocity forever or until acted upon by another force in the opposite direction. Essentially, inventing the conservation of momentum laws and the Newtonian laws of motion in the year 1000. Jump 500 years forward, and Copernicus is flipping the heavens around and changing how we view our place in the universe, which necessarily means questioning why things fall down, if the center of the Earth system is actually the Sun in the center of a solar system. If Earth is essentially in the celestial sphere of the Sun, which we can now call the planetary orbit, then why do rocks fall down if Earth is not at the center? Now, somehow, it is the rock that moves around the stationary fireball. We can, for the most part, just agree with Aristotle still, and say, well, fire goes up to naturally exist with the sun, and the rocks fall down to be with the earth. But in order to do that, we'd have to ignore Avicenna. That's fine, said the church. We will pretend he doesn't exist. In 1609, Kepler published his book called A New Astronomy, which includes the first two laws of planetary motion and states that the true theory of gravity rests upon the following axioms. Every corporeal substance, to the extent that it is corporeal, has been so made as to be suited to rest in every place in which it is put by itself, outside the orb of power of a kindred body. Gravity is a mutual corporeal disposition among kindred bodies to unite or join together. Thus, the earth attracts a stone much more than a stone seeks the earth. The magnetic faculty belongs to this order of things. Heavy bodies, most of all if we establish the earth in the center of the world, are not drawn towards the center of the world because it is the center of the world, but because it is the center of a kindred spherical body, namely the earth. Consequently, wherever the earth be established, or whithersoever it be carried by its animate faculty, heavy bodies are drawn to it. If two stones were set near one another in some place in the world outside the sphere of influence of a third kindred body, these stones, like two magnetic bodies, would come together in an intermediate place, each approaching the other by an interval proportional to the bulk of the other. Galileo tested experimentally the effects of this gravity by rolling balls down ramps. Galileo got a very small inclined ramp. The small incline meant that the ball was not going to be as affected by air resistance, which becomes more apparent the steeper the drop. Likewise, Galileo knew that if you dropped a ball from a short height from the ground, the impact the ball would make with the ground would be small, as compared to when you drop the ball from a high height. The higher the ball, up into a point, the harder it hits the ground, and therefore, something is happening here. Galileo did not have clocks, or cameras, or lasers, etc. So in order for Galileo to measure the rate of the balls as they rolled down the ramps, Galileo used water leaking at an equal rate from a vessel, and then measuring the weights of the water that was released in the amount of time the balls were rolling. Galileo found that the amount of weight in the cups was changing between certain intervals. For example, when he starts the ball at the very top, compared to starting at halfway, the water weight difference is not half as you might expect. In fact, it would take about an equal amount of time for the ball to go down a quarter of the ramp as it would for it to go down the remaining 3/4. And likewise, if you start at the middle of the ramp, it takes about the same time to move a quarter of the way from half as it does from the other 3/4 of that half. It appears as if, in fact, there was a mathematical pattern to the motion, such that we can say that the distance it covers increases over time, aka it is speeding up. It is changing velocity over time. Galileo calculated that distance is equal to the square of the time, such that after 1 unit of time, the distance was 1 unit of length. After 2 units of time, the distance was 4 units. After 3 units, 9 units of distance, etc. Galileo was thus able to place a bell at a distance of 1, 4, 9, and 16 units from the starting point, and as the ball traveled the distance with acceleration, the bells each play at the same tempo. Galileo continued to drop balls of various weights and sizes down various ramps until he proved that 1. Distance is proportional to the square of time for everything, and 2. That objects retain their velocity in the absence of any impediments to their motion, i.e., has inertia. Galileo wrote, "Imagine any particle projected along a horizontal plane without friction. Then we know that this particle will move along this same plane with a motion which is uniform and perpetual, provided the plane has no limits." Some 40 years later, Robert Hooke told Newton about his hypothesis of orbital mechanics and the inverse square law of planetary motion. However, Hooke refused to show his proof and did not publish those results. But Newton did publish his mathematically derived mechanics of Kepler's laws of planetary motion, and then published the hypothesis of the inverse square law of universal gravity, making an enemy with Hooke that lasted the rest of Hooke's life. Newton's publication read, "I deduced that the forces which keep the planets in their orbs must be, reciprocally, as the squares of their distances from the centers about which they revolve, and thereby compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the Earth, and have found them to answer pretty nearly." End quote. The force of gravity is proportional to the mass of object 1 times the mass of object 2 divided by the distance from their centers squared. This is the universal law of gravitation, and it states that every particle attracts every other particle in the universe with a force that is proportional to the particles' masses and the distance between their centers of mass. This formula cannot, however, be used as an accurate equation until we find the gravitational constant, that rate of gravity which is true everywhere. G is the constant of proportionality attracting any two bodies from anywhere in the universe. The tension in the ether, if you will, the spring tensions of the ether of Hooke's, or the tension in the lines of force of Faraday, who historically here is yet to come. It was this confusing little constant of proportionality that made people skeptical of Newton, for he is essentially stating that there is an atom on a planet in the star system of Proxima Centauri which is attracted to an atom in you. In fact, to every atom in you. By what means was there to suppose this action at a distance, his colleagues scoffed. Newton, however, didn't really care about that, because he didn't need to postulate a hypothetical ether in order to account for his ideas. He had math, and the math worked every time. Well, not every time, but we will get back to that later. We needed to find this gravitational constant to make the calculations really accurate. Knowing the approximate mass of the sun and planets, and their distance between each other, provided great measures without the constant, but to predict things to the degree, to a second, would require more precision, and the fact of the matter is that not having a constant will always lead to failure. The constant must exist. Enter Henry Cavendish, who found a way to measure the gravitational constant. An elaborate setup which was a type of replica to Coulomb's torsion balance experiment. As the formulas are identical, so too is the experimental setup, kind of. A torsion balance holding two 350-pound lead balls, suspended opposite from each other, which had two smaller 2-pound balls positioned around the larger balls. The smaller ball's attraction with the larger ball was the main focus of the experiment. The use of two each is to balance on the torsion wire. As the smaller balls and larger balls mutually attract one another, this puts tension on the suspension string, which causes the suspension string to twist. The structure eventually comes to an equilibrium, where the torque on the wire can provide a measurable value of gravitational attraction. Cavendish's results were not as accurate as we have today, but compared to everyone else in 1797, he was the closest. And he found that the force on the wire was 1.74 times 10 to the negative 7 newtons, and therefore accounting for the masses of the balls and the distance between them, Cavendish found the value of G to be 6.74 times 10 to the negative 11 meters cubed per kilogram second squared. Today, we know that that value is 6.67408 times 10 to the negative 11 meters cubed per kilogram second squared. Two of the mathematical calculations of planetary motion did not work even after Cavendish found the universal constant G, and those were the orbits of Uranus and Mercury. In 1843, John Couch Adams and Urbain Jean-Joseph Leverrier independently predicted that there must be another planet, as the discrepancies between Kepler's laws and observations of Uranus were not making any sense. Unless something else was pulling on Uranus from outside the system. Given the orbital mechanics of Newton, if you assume another body must exist, and it does, then you will be able to predict when it is going to pass near other objects. By 1846, the planet Neptune had been discovered, when Leverrier sent his colleague the position in the sky to look, and that colleague, Godfrey Gale, found the planet right where Leverrier said it would be. Mercury was then the only object that Newton's laws could not fully account for. So many speculated another planet closer to the Sun, and they chose the name Vulcan, for the Roman god that forged the weapons of the other gods in his furnace under the island of Volcano. This brings us right back to Lorentz and Einstein, so we return to Einstein in 1907. In 1907, Einstein assumes, quote, the complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system, end quote. And, by doing so, also predicts that clocks dilate due to gravity, and that light should bend in the presence of a gravitational field. He did so by extending the principle of relativity to an object with a constant acceleration. A constant acceleration means that the velocity changes over time. If you imagine a frame of reference which is moving with the object, both of which are moving relative to the stationary frame of reference, we could imagine putting a velocity frame of reference at the location of the accelerated frame for each unit of time. If we restrict ourselves to the small changes in the beginning and set them all together at t equals 0, then after the first click, the s' frame and the sigma frame are now in location 2 together. If we synchronize our clocks in the s' frame, we know by special relativity that for this to be perceived as true for people on s', then people on s will calculate the front clock as being behind in time and the back clock as being ahead in time. After the next unit of time, sigma no longer matches s' or s. When the s' and s' frame calculate the difference of sigma's local time from their perspectives, they find that the local time of the object is equal to the total of the other two times, call it tau, times 1 plus the acceleration over c squared, times the distance from the observer. However, from the point of view of a single object that spans that length and exists in the frame of sigma, it is required to use the time tau, which appears as a normal functional clock to them. Einstein, having already assumed that we cannot tell the difference between being in an accelerating frame of reference and gravity, shows that we can replace the acceleration of the frame and the distance with phi, the gravitational potential, obtaining that clocks above the ground run faster than the clocks on the ground by a factor of 1 plus phi over c squared. Given this, Einstein then proceeds to show that that fact will have an effect on photons, that gravity will affect photons despite photons having no mass. Einstein showed that momentum is replaced by momentum times this factor, and likewise the speed of light is replaced by the speed of light times this factor. Therefore, Einstein was able to show that light rays that propagate with the x-axis are affected by the gravitational field, and that the light rays which do not propagate along the x-axis are bent by the gravitational field. It is important to note here that this does not mean that the speed of light actually changed, but rather that the accelerating frame's spatial coordinates are changing in a curved manner. The coordinate velocity of light changes, not the speed of light itself, which would be strange given that we need that number to calculate the appearance. This has a very important meaning in regard to Einstein's 1905 discovery that mass and energy are related, and that an object in motion appears to change in kinetic energy. More so, this discovery that even photons will be affected by a gravitational field helps illuminate the answers he was searching for. Einstein had previously stated that if you add energy to the object, for example, forcing a magnet near another magnet that it is repulsed from, that gain of energy will increase its mass. Einstein was now looking to show that if that object is a mass and the energy you add to it is caused by gravity, that the result will be the same. Given all of the above conclusions of special relativity, Einstein concludes the paper stating, quote, "This equation expresses the principle of conservation of energy and contains a very remarkable result. To each energy E in the gravitational field, there corresponds an energy of position that equals the potential energy of a ponderable mass of magnitude E over c squared. Thus the proposition that to an amount of energy E there corresponds a mass of magnitude E over c squared holds not only for inertial, but also for gravitational mass. End quote. In 1911, in the paper titled On the Influence of Gravitation on the Propagation of Light, Einstein expanded the views he established in 1907, including postulating in the introduction of that paper that one can test his hypothesis by looking for rays of light passing near the sun, and you will find that they are deflected by about 1 second of arc. In this 1911 paper, Einstein shows that the gain of inertia mass from a gain of energy is identical to the gain of gravitational mass from a gain of energy, and that it is in fact the principle of relativity that merges the principle of conservation of mass into the principle of the conservation of energy. Given this, he states that if you send radiation energy from a high position above the ground down to the ground, and assume there is no gravity, but you find a way to accelerate the object to the ground, then, given the special relative nature of clocks and lengths, the energy that the ground receives will be greater than the energy sent. And by that same argument, the speed of light, c, at ground, should appear to be equal to the speed of light on the ground plus the speed of light at a given gravitational potential phi divided by c squared. And, therefore, he writes, quote, "The principle of the constancy of the velocity of light does not hold good in this theory in the formulation in which it is normally used as the basis of the ordinary theory of relativity. That the velocity of light in a gravitational field is a function of place. That light rays propagated across a gravitational field must undergo deflection." Einstein then states how we must model this by returning to a plot where light is constant, and through Huygens' principles of light, we deflect a plane of light by using circles and taking the flat spacetime, and we get the angle of deflection. Einstein then concludes that, quote, "A ray of light traveling past a celestial body undergoes a deflection in the direction of decreasing gravitational potential, and thus in the direction towards the celestial body." Everyone wanted to prove this was either true or false, and given that they had stars and a sun nearby, it seemed pretty simple. First, we just need a solar eclipse, so that the sun does not blind us when we look near it. Then we just need to measure where the stars behind the sun are. Then we wait for the sun to move from in front of those fixed stars and check again in 3 months to see if the relative distance between them changed when there is a massive object between them and us. Well, it was not that easy, because if you do any astronomy, you know that clouds will ruin everything. In October 1912, during the first solar eclipse available, it rained. So they tried again August 21st, 1914, and again, clouds. Then, and you'll know why if you are a bit of a history buff, you'll notice that the next few years of science into the angle of deflection of light caused by massive celestial bodies stopped in order to start working on science for projectile weapons and flying machines and big heavy armored vehicles. In 1916, Einstein proposed 3 tests for general relativity, which subsequently became called the classical tests. The first was that the general theory of relativity properly calculates the precession of Mercury's orbit, predicting an extra 43 seconds of arc in its precession. Second, light will be deflected by the sun. Third, that light escaping from a star or planet will be redshifted, meaning its wavelength will appear more in the red section of the visual light spectrum. It was already established by 1882 that the measured precession of Mercury was approximately 43 seconds of arc. In May 1919, Arthur Stanley Eddington was able to prove Einstein's second test for general relativity, finding the light from stars of Taurus from behind the sun that had deflected at the angle that Einstein had predicted. Finally, in 1925, results for measuring the star Sirius proved to have been redshifted. In 1959, the Pound-Rebka experiment proved Einstein's gravitational time dilation here on Earth. Einstein's theory of general relativity was also able to predict the cosmological constant, universal expansion, the Big Bang, the cosmic microwave background, black holes, and gravity waves, all of which have been demonstrated beyond a reasonable doubt today. Thanks to these discoveries, global positioning satellites are able to keep proper time on Earth by adjusting their on-board atomic clocks with a special and a general relativistic shift to counteract the velocity and gravitational potential of the satellite and its clocks. If it were not for Einstein's general theory of relativity, any satellite we threw up into space with a clock on it would very quickly become out of sync with our clocks on the ground, and our GPS would tell us to drive into the ocean. If that which Einstein's general theory of relativity predicts does not actually exist, then the global positioning satellites above Earth would have no reason to time dilate. Putting it all together. From Earth, without ever leaving the planet, it appears that the Earth is flat, and when you walk all the way around it, your feet never leave the ground and start walking on the ceiling for half of the trip. So it appears to you to be horizontally in front of you forever. But if you leave the planet and go hang out on the moon for a while, and you watch your friend walk around the planet, you see him walking around a ball, like a bug on a basketball. Likewise, up close, i.e. locally, all experiments of light are in a flat spacetime, and it's at its universal constant velocity, moving in a straight line. If you get a global picture, however, things start to become a little more complex. Given that we are doing our experiments on Earth in relatively tiny observatories, we cannot see the curve, just the final results, which appears to us as to have arrived in straight lines. Mathematically, then, we need to include a thing which prevents us from forgetting that the universe is not entirely flat, which will keep our lengths accurate to reality. The mathematics required to move between flat and curved spacetime are tensors, which is not something we are going to get into. All that needs to be said here is that a new metric was formulated which captures all of the geometric and causal structures of the space-time ether, meaning that it can be used to define notions of time, space, distance, volume, curvature, angle, and temporal separation. Einstein required using this new form of mathematics in order to better describe the universe. Starting then from the very beginning, if you are a mass, then that means you are composed of atoms or pure energy. We are made of atoms. Atoms are just regions of the ether which are stable and bound tightly in a tiny space which cannot be occupied by different energies of the same kind, in the same time and in the same respect. The stability of the atom is caused by atomic forces which interact and change, and this means everything with mass also has frequency and therefore is also a clock. All masses are thus their own type of clock, which always interact at the speed of causality. The speed of the ether interacting with itself is what allows for that stability of the atom, of that mass, of that clock. Now your atoms send that energy around through the use of photons. Photons always travel at a constant velocity c, in vacuum. If an atom in your foot shoots out a photon that is absorbed by an atom in your head, and you are in a box, and that box is said to be motionless, as you are not moving while it is on the surface of Earth, then you know that the length the photon traveled was your height. And given your height and the constant velocity of light, you can calculate the time duration. If, however, your box is in empty space, moving upward at a constant velocity near the speed of light, then the photon from your foot atom will still be traveling at a constant velocity c, and will still pass you by at c. If you think about how this could be, it is only possible if the photon from your foot was traveling for a longer amount of distance, the distance to the original place of your head, plus the distance moved at the box's velocity. And if the clocks of your foot atom and your head atom are synchronized, such that to an atom in your torso, it receives the photons of the foot and head at the same time, meaning that the foot photon clock is ahead of schedule, and the head clock is behind schedule, such that the longer distance of the foot photon matches the clock of the shorter distance of the head photon. The torso runs into the head and runs away from the foot. Thus, to be seen at the same time requires different set times. If, however, your box is an empty space moving upward at a constant acceleration, acceleration is an absolute state of motion, and everyone inside and outside of the accelerating frame knows which frame is accelerating and by how much. For example, if you have 4 boxes moving in space, one is with us. We are considering a stationary rest frame. 2 are moving at a constant velocity, one moving from below us to above us, the other moving from our right to our left, and one is accelerating. The effect of relativity is that we cannot tell the difference between a motionless frame, like ours, and a moving at a constant velocity frame, like boxes 2 and 3. And so, when we see our accelerometer, it is a box with a ball in the middle, held in place by springs. When we look at the accelerometers of one of the other velocity frames, those balls are also in the middle of their boxes, despite us seeing them moving and expecting a little tension on the springs in the motion of that direction. Comparatively, when we look at the frame that is accelerating, we all see, including the people in that frame, that the accelerometer is stretching the spring at the top and compressing the spring at the bottom, and curving the springs at the sides. That is the sign of acceleration. And using Hooke's spring equation, we can calculate the force applied to the springs by measuring their new lengths. From all perspectives, then, we know that if you are accelerating upwards in your box when your foot photon sends its signal up to your head, then your foot atom, which has a mass, would lose energy, as we had seen in Einstein's last 1905 paper. By those same acceleration and special relativity ideas, the photon itself loses energy as it races to catch up with your head. After each second of the atom's clock, we imagine a new velocity frame of reference, which is changed drastically by the next time unit. But as photons cannot lose velocity, the loss of energy is within the photon's wavelength. And the wavelength stretches into the red part of the visible light spectrum, which is why we call it redshift. So long as you are in a uniform field of acceleration, the photons from your foot are going to lose energy when they reach your head, if it has the energy left to be seen. And as Einstein showed in the photoelectric effect, a photon with the wrong quanta of energy cannot excite the atom of the receiver. In the reverse manner, the atom in your foot would be receiving the photon with more energy, and the clock is moving much faster than theirs. This is different from constant velocity frames, where each observer sees the other experiencing the same phenomenon. E.g., in the constant velocity setup, if Alice sees Bob's clock as slow, then Bob sees Alice's clock as slow. But here in the accelerating frames, if Alice sees Bob's clock as slow, then Bob sees Alice's clock as fast. We can detect acceleration. Finally, if we cannot tell the difference between a uniform constant acceleration field frame and a uniform gravitational field frame, then special relativity holds for both. And therefore, a uniform gravitational field is equivalent to a uniform constant acceleration field. We know, however, that the gravitational field of Earth is not itself an accelerating frame of reference. For, say if the Earth were flat and accelerating upward at 9.8 meters per second squared, it would only take a relatively short time for the Earth to surpass the speed of light and continue accelerating past the speed of light, in which case nothing in the universe could ever causally interact, in which case we could not be having this conversation. Therefore, we are in a gravitational field, not an accelerating frame. And therefore, clocks on the ground of Earth tick slower than clocks at the top of a skyscraper. The equivalence principle therefore now states that a frame of reference experiencing a non-rotating free fall occupying a small region of spacetime, the laws of physics are those of the special theory of relativity. We can add to our list of principles, then, that the equivalence principle is valid. Finally, we must account for one last thing. The fact that we do not live in a uniform gravitational field in a global sense. Just from large scales, it is clear that to the people in America versus the people in Australia, up and down are, relatively speaking, in opposite directions. And this is true too for people in Ecuador versus people in Indonesia, which are not the exact same ups and downs as they were for the last two. The Earth is a sphere, kinda, so the downward field lines point radially inwards. And the acceleration you experience on the ground is coming from the ground pressing up against you. Mass is a kind of energy. Regardless of its size, a mass is composed of energy stuff, which can release and absorb energy. The fact that the universe is not entirely dark, the fact that there are stars, is proof that the plain light waves of energy from billions of stars are passing by you at every moment. And so it is safe to assume that if you can see that starlight, that your atoms, your mass, can absorb starlight, and therefore you were struck by a tiny amount of that star's mass, which is converted into momentum, which would cause your atoms to recoil a bit when receiving them. Therefore, you experienced a force. Therefore, you experienced a moment of acceleration. So two masses floating near each other in empty space will be experiencing tiny accelerations from photon momentum, and therefore also re-release that energy with tiny acceleration. Therefore, clocks closer to them tick slower than clocks further away. So everything with mass also has its own gravity, which we can express as meaning anything with mass interacts with the ether in such a way that time dilation bubbles around it. If you were to draw this as a Cartesian coordinate system, accounting for special relativity, you would create a world-line space-time diagram. And the fact that these mass-time dilation bubbles exist maps onto the graph by making the appearance of curving lines, either in the motion of the accelerating object or in the fabric of the graph itself, combining together the fact of the gravitational time dilation bubbles around masses with a conceptual framework which is currently available to our 2 to 3 dimensional graphing language. One can show for a fact that gravity, the falling downness, is not itself a force, as it is identical to not experiencing a force at all in empty space. Anything that is equivalent to floating in space with not a single object or force field around it for billions of miles can be said to be caused by force. So falling down, the effect of gravity, is not a force. All we currently have, conceptually speaking, is analogous to curvature, to the markings of a line on a space-time diagram. And therefore objects which naturally move at constant velocities experience a change in time when they pass by a time dilation bubble. And due to the consequence of special relativity, the object never experiences a change in time, but rather, that change is expressed as a change in space, and the object falls down. Therefore, for all intents and purposes, we conclude that gravity should be considered, in the conventional sense, the manifestation of a curvature of the space-time ether, which itself is induced due to the presence of matter. This is the central tenet of the general principle of relativity, and so too will we add it to our list of principles, that the general theory of relativity is valid. Unfortunately, well, maybe fortunately, I think we're all having fun here, we're not quite done. Well, we are done for this video, but there is another aspect to this history that is very important for both the flushing out of the ideas that support these relativity videos, but also important for the future of physics. We need to talk about the history of quantum. Next time.
you.